Bismillahirrahmanirrahim. We continue our discussion in software engineering and will discuss further more concepts within software design concepts and principles. This was the chapter that we had started in the previous lecture and will carry on this discussion where we had left from the previous lecture. Before proceeding ahead, let's have a recap of the points that we had already discussed in the previous discussion. In previous lecture, within this chapter, software design and concepts and principles, we developed an understanding with the term software design. Software design is actually the meaningful representation of the software that is going to be built. So it is a sort of a blueprint that you generally develop for your house when you are to construct a house. Then we discussed the relationship between software design and software engineering, in which we had seen that software design is the first technical step within the software engineering. This is the first technical step. Before that, we had done a phase that was requirement analysis, and the output of requirement analysis was the data model, functional model, and the behavioral model. And those models are then converted into different types of designs. 4 different types of designs, or we can say design phase, can be subdivided into 4 different sub-design phases. The first design is the data design, which is generally developed on the data model which have been created in the previous phase, which is the requirement analysis. So data model is converted to data design. The next design phase is the architectural phase. The architectural phase is the functional model which has been developed in the requirements analysis phase. So functional model is then converted to architectural interface. Third level is the interface design, or this is the third sub-design phase, in which we design different interfaces, how user would interface, how user would interact with the system, how your software will interact with different other components in your system. So an interface design is then developed, while the last phase or the last sub-design phase is the component level design, in which we design different modules, different functions, different units or different components of your system. 4 different designs are then developed. We also discussed in previous lecture the design process. In design process, the main focus is given on software quality. As we said, a good design is the guarantee of a successful software, or a guarantee of a good software. So design must be assessed for software quality. So we had discussed different quality factors for software design that ultimately resulted in the goals of software design. 3 different objectives for good quality within design were discussed, that include your design must implement or must discuss all the implicit and explicit requirements of the customer. The second objective was the design must be readable and understandable, and the last objective was that the design must show the complete picture. So these were the points that we had already discussed in the previous lecture. In today's discussion, we are going to discuss now different design subcategories. As we had already said, design phase has been divided into 4 sub-design phases, in which we have to develop 4 different types of designs. data design, architectural design, interface design, and component level design. So in today's discussion, we are going to discuss different categories, these subcategories of design phase. So the first subphase of design phase is the data design. Now, what is a data design? Like other software engineering activities, the data design, which can also be referred as data architecture, creates a model of data and information that is represented at high level of abstraction. So it is the creation of models of data and information generally presented at high level of abstraction. Level of abstraction is generally the customer or the user's view of data, how user is looking at the data. This data model is then refined progressively. More implementation specific representations that can be then processed by the computer system. So this abstract design is then refined iteratively into implementation specific details. The structure of data has always been an important part of software design. At the program component level, the design of data structures and the associated algorithms required to manipulate them is essential for the creation of high-quality applications. At the application level, the translation of a data model into database is essential to achieve the business objectives of the system, while at the business level, the collection of information stored in disparate or separate databases and reorganized into a data warehouse enables data mining or knowledge discovery that can have an impact on the success of the business. So in every case, data design plays an important role. So the data objects defined during previous phase, which was the requirements analysis, are modeled using different techniques such as the entity relationship diagrams and then the data dictionary. So the data objects defined during software requirements analysis phase are then modeled using entity relationship diagrams and data dictionary. The data design activity translates these elements of the requirements model into data structures at the software component level, and when required, at a database architecture at the application level. If required, if database is not required, then it is not developed. In the past few years, data architecture was generally limited to data structures at the program level and databases at the application level. But today, businesses, large or small, are more dependent on data. It is not unusual for even a moderately sized business to have dozens of databases serving many applications encompassing hundreds of gigabytes of data. The challenge for a business has been to extract useful information from this data environment, particularly when the information desired is cross-functional. So to solve this challenge, the business IT community has developed data mining techniques, also called knowledge discovery in databases, that navigate through existing databases in an attempt to extract appropriate business level information. However, the existence of multiple databases, their different structures, the degree of detail contained within these databases, and many other factors make data mining quite difficult within an existing database environment. So an alternative solution is developed known as data warehouse that adds an additional layer to the data architecture. Now, what is a data warehouse? It is a separate data environment that is not directly integrated with day-to-day applications, but it encompasses all data used by a business. In a sense, a data warehouse is a large, independent database that encompasses some, but not all, of the data that are stored in databases that serve the set of applications required by a business. So mainly within a data design phase, the more focus is on the representation of data structures or organizing data and developing relationship between different data objects in terms of entity relationship diagrams. The output of this phase or this design subphase is generally entity relationship diagram or data dictionary or data warehouses. Now the next subcomponent or subphase of design is the architectural design. Since when we're discussing the evolution of design process, we had discussed that currently software design focuses mainly on the architectures and the patterns, how design will be generated. So instead of focusing on structures, instead of focusing on organization of data, the more focus is now given on the architectures and the patterns, how design will be arranged in different patterns. So now let's see what is an architectural design. The architectural style is known as a pattern for construction. The software that is built for computer-based systems also exhibits one of many architectural styles. Every style describes a system category that encompasses, number one, a set of components that perform a specific function required by the system. Number two, a set of connectors that enable communication, coordinations, and cooperations among these components. Number three, the constraints that define how components can be integrated to form a complete system. And number four, the semantic models that enables a designer to understand the overall properties of a system by analyzing the known properties of its constituent parts. So these are the four elements of an architecture. Millions of computer-based systems have been created over the past 50 years. The vast majority can be categorized into one of a relatively small number of architecture styles that we are going to discuss next. The first common architectural design style is known as the data-centered architecture. A data store, for example, a file or a database, resides at the center of this architecture and is accessed frequently by other components that update, add, delete, or otherwise modify data within this store. So here you can see the figure of this architecture style. The client software accesses, these are different client software. This is the central repository. Here you can see a central database, and all these are the client systems, the client softwares, the client applications. These are all client softwares that are accessing this central repository or central database. So the client software accesses the central repository. In some cases, the data repository is passive. That is, client software accesses the data independent of any changes to the data or the actions of other client softwares. A variation on this approach transforms the repository into a blackboard that sends notifications to client software when data of interest to the client changes. Data-centered architectures generally promotes integrability. That is, existing components can be changed and new client components can be added to the architecture without concern about other clients. So, integration is possible within data-centered architectures. Some of the clients can be removed easily and others can be added easily. Data can be passed among clients using the blackboard mechanism. That means the blackboard component serves to coordinate the transfer of information between different lines. Client components independently execute processes. So the data is stored here in the center repository and clients accesses that data and then can perform actions on that data. The action is generally performed at the end of client application. That means on the client machine while data is being accessed or stored at the central repository. This is a very common architectural style, commonly used for the databases. The next architecture style is known as the data flow architecture. This architecture is generally applied when input data is to be transformed through a series of computational components into an output data. If input is to be transformed into series of actions into an output data. So this structure is then required. The common pattern is known as a pipe and filter pattern, which is a very common pattern of data flow architecture. Here you can see the diagram of pipe and filter architecture. It is a set of components called filters. Here you can see these are the components, or these are components mean these are the functions which can manipulate or change or act some sort of action on the data. These are the filters. Connected by pipes that transmit data from one component to the other. So these arrows here, you can see these are the pipes that are connecting or transferring data from one filter to the other. Every filter works independently of those components upstream and downstream, is designed to expect data input of a certain form and produces data output of some specified form. However, the filter does not require knowledge of the working of its neighboring filters. So every filter or every component, filter is generally a function that is actually acting some activity or some function is being performed on data. A data is given in some form, it has been manipulated by one of the filter, generated output, and that output is then taken to the next filter by the pipes. So every filter is working independently. They are unaware of the activities being performed by other filters. The next design pattern within data flow architecture is known as the batch pattern or the sequential pattern. So if the data flow degenerates into a single line of transforms, then it becomes the batch or sequential pattern. Here you can see when it becomes in a single line of stream, this then becomes batch or sequential. Here you can see in the pipe and filter, data is moving either downstreams or upstreams at different levels. But when data becomes in single stream, then it becomes either sequential or batch. So this sequential pattern accepts a batch of data. Batch of data means a group of data, and then applies a series of sequential components. Series of sequential actions are then performed on that data in order to transform it to some output. So these here again filters are, you can see the filters in a sequence. Here you can see filters in a sequence, and the arrows are generally the pipes. So here input goes from one filter to another, changes the form of input, and ultimately an output is generated. This is in sequential fashion. While in pipes and filter, here you can see data, all the data may not move in through all the filters. Some of the data here you can see as they can either move from this sequence to this path, or some of the data can move in this path, the second middle part here you can see, and some can move into this, the third part, depending on the condition, and it can then revert again from here you can see. While in sequence, all the filters are responsible to act on the data that is being passed on to it. While in the pipes and filter, some of the filters may act while others may not, depending on the condition being placed on data processing. The next design architecture is known as the call and return architecture. This architecture style enables a software designer to achieve a program structure that is relatively quite easy to modify and scale. So it has a number of substyles within this category. For example, the most common one is known as the main program and subprogram architecture, as you would have used this architecture in tree structure when you were discussing the data structures, or when you were designing your program, when you were developing a code for your program. So main program and subprogram is the most common architecture for call and return structures. Here you can see this is the main program. The main program then calls three different subprograms. These subprograms can then call some other respective subprograms, and so on, forming a tree or a hierarchy. So main program and subprogram is the common architecture. This classic program structure decomposes a function into control hierarchy, where the main program invokes a number of program components, which in turn may invoke still other components. The other common type of architecture within this category is known as the remote procedural call architecture. The components of a main program or subprogram architecture are distributed across multiple computers on a network. So when you are using remote procedural call architecture, that means different computing components or functions are distributed over different computers. So when some function is required to be applied on data, and if that function is not present on your computer, so that function is called remotely on some other computer, that function is then executed on your data, the results are then returned to your computer. This is known as remote procedure call, when you call a function on some remote computer. But again, the architecture is similar to function main program and the subprogram structure. The other architecture is known as the object-oriented architecture. The components of a system encapsulates data, and the operations are generally the methods or functions that must be applied to manipulate that data. You might have used the object-oriented programming, in which you define a structure for your program, where you place data and functions, encapsulating them in some form. Some data is kept hidden as private, while the functions are generally kept public. Those functions are used to manipulate the data which is being hidden. So this is the object-oriented architecture, or object-oriented is a complete programming paradigm in which you hide the data and the functions that act on that data. So you must have used this architecture when you were studying the object-oriented programming. The communication and coordination between the components within object-oriented architecture is generally accomplished through message passing. The components are mainly the methods or functions which you define as public within object-oriented programming paradigm, while the data are generally hidden as private. The next common architecture is known as the layered architecture. The basic structure of layered architecture is shown in this diagram. Here you can see this is the diagram for the layered architecture. A number of different layers are defined. Here you can see the first layer, second layer, third layer, and fourth, so on, whatever layers are required. Every layer accomplishes operations that progressively becomes closer to the machine instruction set. At the outer layer, this is the first outer layer, here you can see in the black one, that components service user interface operations. So the first layer is mainly for the interaction with the user. The next layer, the inner layers, these two inner layers, the light gray shade and the dark gray shade, these are the inner layers. So the inner layer components performing operating system interfacing. So different inner layers then work to interact with the operating system and make it understand what activities customer or user requires. Intermediate layers provide utility services and application software functions. So the second layer is responsible for interacting with your operating system, and the next lower layers, so on, then are mainly responsible for providing the utility services to user and generating specific application software functions. These architecture styles are only a small subset of those available to the software designer. So these 5 architecture styles are the most common one that we discussed, though there are many others, but these 5 are the most commonly used by the software architectures to design the softwares. Once requirements engineering uncovers the characteristics and constraints of the system that is going to be built, the architectural pattern or style or combination of patterns that best fits those characteristics and constraints are then chosen. In many cases, more than one pattern may be appropriate, and alternative architecture styles might be designed and evaluated. So one software may not depend wholly on a single architecture style. Different combination of these 5 styles may be used for a single application, or the other architecture styles which we have not discussed in these common type of styles may also be evaluated if they are suitable to be adopted. That is all for now. In today's discussion, we discussed 2 types of sub-design phases, that is the data design and the architectural design. We'll be discussing 2 more sub-design phases, which is the interface design and component level design, in the next lecture. In data design, we actually design the data objects and their relationship with one another. We try to give structure to the data in shape of entity relationship diagram and organize it in subforms, such as in subtype of data structures. Then we discuss the architectural style or the architectural design. In architectural design, which is the most common sort of design in current software design paradigm, different architectural styles are then given to the software that is going to be built. We discussed different common type of architectures, that is commonly used in different applications. That is, the data-centered architecture, in which the client-server model is the most common sort of the data-centered architecture. Then we discussed another architecture, which is data flow architecture, such as the pipes and filters. Then call and return, which is the most common type of structure when we use the programming. The main program and subprogram sort of structure is known as the call and return architectures. The object-oriented architectures are becoming very common, in which we encapsulate the data and functions under one cloud. And then the fifth architecture is the layered architecture, which is generally implemented at the application level or the utility level. The operating system architecture is generally designed in layered fashion. You can also design your applications in layered fashion, depending on whatever style or architecture is suitable to your application. That particular architecture style is selected. It may happen that one single style may not be suitable for a single application, so a mix of architecture styles can also be then selected in order to design a proper software design. So some of the components will be following one architecture and other components may be following some other architecture. If these 5 architectures are not suitable to your application, other alternatives can then also be designed and then evaluated. This is not hard and fast rule that these architecture styles should be followed. It is an innovative thought of the software designer or the software engineer to have a properly suitable architecture style for the software that is going to be built. That is all for now. We'll continue our discussion on the categories of software design in the coming lecture and discuss further more sub-design phases. I thank you all.